how much of time, relatively, of life of a star is spent on the main sequence? Give me a percentage. 90%. Okay, that leaves 10% for the end of its life. Okay. Stars come in different masses, right? The more mass, the more what? The more gravity. The more what else? Think about your HR diagram. The more massive it is, the more massive it is, what else?
Pressure.
The more pressure, because it's got more fusion that's happening, so it's going to burn hotter, right? Therefore, more pressure, which means it'll also be hotter. It'll also be what other property?
Right.
Brighter. And it will last on the main sequence shorter. Okay, don't miss that. So if we were to look at our HR diagram, stars that are over here last the longest. Stars that are up here last the shortest, and it's exponentially different. It's not a linear relationship. Everything else on here, we've kind of been doing linear in terms of like mass and brightness and stuff like that, but time spent is not linear, right? I've not prayed. Let me pray. Heavenly Father, help me to be just clear and concise about things that I've studied and to be able to relate them to everybody here. Father, help it to be interesting. Lord, it's just fascinating to see how you've made the universe and how these different atoms and things have come to be. I pray that we would find interest and joy in learning these things, and that we'd learn them well for your glory and our good. We pray in Jesus' name. Amen. All right. Y'all are familiar with this. This line that everything's on, we call it the main sequence, right? True or false? A star changes spots on the main sequence. False, right? It does not change spots here. True or false? It changes spots on the diagram. True, right? From here it will go to the up, right? What do we call this? The red giant. It'll go to the red giant phase, right? Okay. All stars leave the main sequence and go to that phase, right? When do they do that? What's the seminal event in their lives that caused them to leave the main sequence? Or you could say another way, what's the characteristic of every main sequence star? What's it doing? What makes it a main sequence star?
Fusing hydrogen into
It's fusing hydrogen into helium. Where?
in the core.
In the core. Okay, in the core. Let's go back and think about that for a second. In every star, the center is the core, right? And this is where the fusion's happening. Then you have the radiative zone, then you have the conductive zone, right? And so radiative, we're just going out. Conductive, it's going up and coming back. I'll just write conductive. Right, and this is radiative. And of course then we have what? We've got the chromosphere, and you've got, you've got the photosphere, the chromosphere, and then you've got a corona. Okay? Okay. Fusion's happening here in main sequence stars. Tell me this real quick. What is the corona made of? What element, primarily?
Helium?
Which, not helium,
Hydrogen.
hydrogen, primarily. This one?
Hydrogen.
Hydrogen, this one?
Hydrogen.
Hydrogen, this one?
Hydrogen.
This one?
Hydrogen.
Primarily hydrogen, until the end, because it's fusing hydrogen into helium. By the time it's done with the main sequence, the core is made up of helium. Okay? Over time, the hydrogen is fusing into helium. Okay? When it leaves here, that's what you get. But what's the rest of this still made of? It's still made of hydrogen. Okay? That's important. Just because a star is a giant star does not mean it doesn't have any more hydrogen. It just means it doesn't have any more in its core. Okay? All right. So main sequence stars are fusing hydrogen into helium. Now you threw out there helium out here. I paused. It's primarily hydrogen, right? Like 75% hydrogen, but that doesn't mean there's no helium. Okay? There can still be helium out here. But 75% or so of a main sequence star is likely to be hydrogen. when it stops fusing hydrogen into helium, it's going to ultimately leave the main sequence. And we spent a good amount of time talking about this over the last 2 classes. There are 2 things that are happening inside every star. I don't mean its core, but I mean the star as a whole, right? You guys know these by now. The line pushing in is gravity. The line pushing out is pressure. All right, so gravity's pushing in, pressure's pushing out. What's causing the pressure? Fusion. The heat of fusion in the core is constantly pushing these outer layers out. Gravity from all that matter is constantly bringing those outer layers back in, and so they're in this dynamic equilibrium. Yes, there's a little shifting back and forth, but most of the time on the main sequence, it's relatively static. It's not getting much bigger, it's not getting much smaller, okay? That's true until we're out of hydrogen. E equals mc squared. It says that energy equals mass times the speed of light squared, right? It's the conversion of mass into energy. We know, you go back to like week 2 of this class, that as we fuse hydrogen into helium, we lose a little bit of mass, right? We lose it to neutrinos and we lose it to gamma rays. It's converted into other things and it takes off. But it's relatively small. It's like 0.7% or something like that of the mass is lost to energy. And so as a star reaches the end of its age, it's still super, super massive. The gravity has not been depleted by very much at all, and yet, at the end of its life, this fusion that's happening in the core stops, because one day we just run out of hydrogen. So, we go back to our diagram here. The gravity doesn't decrease much at all, but this outward pressure, because of the heat from fusion, is gone. And so what's going to happen here?
It's going to push in.
It's going to collapse. It's going to begin to collapse. Particularly the core is going to collapse. And so what you start to see where, you know, we've got our layers right here. These outer layers, they're going to shrink in, but not as much as the core. Okay, the core is going to contract and contract and contract and contract. As it does, it's much like a protostar. Okay, I want you to think about that. Like the core, this is worth knowing. This might be worth writing down. Okay, core of a star leaving the main sequence is much like core of a star coming onto the main sequence. I'm going to explain why in just a moment, okay? Go ahead and get that written down if you would. Core of a star leaving the main sequence is much like the core of a star coming onto the main sequence. So let's think back to our stellar evolution. You've got a bunch of gas in a nebula, contracts and filaments, you've got clumps, you've got cores, you've got a protostar. At some point I'm going to have a main sequence star. How do I get from all that just gas everywhere to a main sequence star?
Gravity and rotation.
Gravity and rotation are going to contract it in. As the gravity contracts it in, it starts to heat up. The force of gravity, the energy of gravity causes it to start to heat up. When it hits the right temperature, nuclear fusion begins, right? Until that happens though, there's only one pressure, there's only one force in that star, and it's the force of gravity. It's contracting it and it's heating it. Until eventually fusion begins and we go into this equilibrium, right? That's the same thing So what was happening here is the same thing that's happening up here. Except it's not hydrogen now, it's helium. The gas in here is contracting, 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 contracting due to gravity until it gets so hot that it ignites again. Okay? And it does it, they refer to it as the helium flash. It happens like a runaway train. I mean, like it just begins. It hits the right temperature, and when the helium reacts now or begins to fuse into other things, it creates this burst of energy, and all of a sudden helium's fusing everywhere, all throughout that core. Okay? That's it. As this core is contracting, it's heating, right? The layers of hydrogen around it were almost hot enough to fuse already, but they weren't quite hot enough to fuse. Well, as the core heats up, that energy radiates out, it heats up the outer shell, and now that outer shell begins fusion of helium, from hydrogen into helium. We can kind of walk you through this stepwise, okay? So during its main sequence, fusion's happening in the core. This layer right outside the core is super hot, almost hot enough to fuse, but not quite in that radiative zone. Right after this stops, the core is going to begin to contract, right? As it does, it's heating up this outer layer, right? This next layer that was right here, I'm going to draw the same kind of thing here. I'm going to draw it in dots, okay? This outer layer was almost ready to begin fusion, but not quite. As this core contracts and heats up, it adds energy to this layer that was already incredibly hot. Yes, sir?
I actually gotta go.
Okay.
I have something I need to do.
All right, good. Now, this layer is going to begin fusion, right? So, when it does, the core is still continuing to contract, but this layer is going to begin fusion. When it does, it adds pressure to the rest of this, right? And that pressure is going to push these outer layers out. And so all of a sudden, we're going to go from here to here to here. And now we're at the red giant phase, right? During this phase, my core is still going to continue to contract. As it contracts, it heats up. And of course, I've got my fusion. I've got my red giant. Until this contracts enough and gets hot enough that there's enough energy to fuse helium into beryllium and into carbon. And when that happens, it's referred to as a helium flash. And that's going to send a burst of energy through the entire core and outer system. And now we actually become stable for a little while. And the core stops contracting. These outer layers stop expanding. And now we've got fusion of helium into carbon and oxygen happening in that core. Now I've still got fusion happening of hydrogen out here. Okay. Does that make sense? We talked about this more or less last class, these stages. Maybe not in as much detail. This is what happens for a star. How do I say this? They compare other stars and their masses to the mass of our sun, because these numbers are for the amount of material, or to do it in kilograms or tons or kilotons. It's just ridiculous. It's way too big for us to even imagine. So they refer to things in terms of the mass of our sun. So every star less than 8 solar masses experiences something like this. Now the ones that are that big, they can do stars that are about 3/4 the size of ours to stars that are twice the size of ours, they do this and they stop. They'll never have enough gravity to generate enough heat to fuse anything higher than carbon and oxygen. And so this is the end game for them. Stars greater than this can fuse hotter and hotter elements, or higher and higher elements, because they have more and more energy. Stars even greater than that go boom, right? And we'll talk about that more, well, not next class because you're having a test, but when we get back from that. So today we're dealing with the ones that go red giant but don't go boom. No supernova here, okay? These will end up producing what's called a planetary nebula. So you got to ask yourself, what happens when I get to this phase and now I run out of helium and I can't fuse anything bigger than this? What happens to it? Well, remember here, we ran out of hydrogen, so we just contracted, and we heated up, and we heated up, and we heated up, and that ignited other layers. But here, there's nothing, there's no more fuel source. So eventually, all this is going to do is cool down, right? The energy of a star comes from fusion. We're converting matter into energy, E equals mc squared, every second of every day, right? But when you run out of a fuel source, you don't have enough energy to get that process, to keep that process going, it stops. Well, what happens to all that material? Slowly begins to drift off into the outer layers anyways. The core will be there super dense, super dense. But those outer layers, remember, we were getting bigger and bigger and bigger and bigger. And there's more to this, as we'll see coming up. Those outer layers are quite far away now. And there's a lot of solar wind, and there's a lot of radiation coming off of the core, and so it sends those outer layers out into space, and it forms what's called a planetary nebula. So the thing we really want to grasp today, the thing that we're covering, is this concept of going from red giant to planetary nebula. Okay? This happens in stars that are about 3/4 to 8 solar mass units. All right, I'm going to turn this on and we'll look at some stuff.
Can I use that?
Absolutely. Let's start with this one. This guy's going to kind of put you to sleep a little bit. I'm sorry for that. I'll try to stop
That's
him.
what happens in a star that has a mass a little bit more massive than the sun, down to the very small mass stars. So after the red giant stage, after the star is small enough and becomes very large. Talked a little bit about what happens when the helium flash occurs and we get the helium main sequence for 100 million years or so. But we have some other questions. There's more to the life of the star. It doesn't stop at the helium main sequence. So what's going to happen here? What's the final end of the star's life? And then some comments on why the final stage of a star's life is different depending on whether it's a very massive star, probably 8 solar masses or larger, versus a few solar masses and smaller. There's a difference in the way the stars die. So we're going through this basic scheme. We have this giant molecular cloud that's cold. Gravity causes the knots of gas to condense, collapse, and as that happens, they heat up. You get protostars visible in the infrared, and then finally that core temperature reaches a place where hydrogen fuses to form helium, and the star is on the zero-age main sequence. The hydrogen fuel is depleted in the core. The helium is not in a place where the temperature is high enough to allow fusion of helium to occur. So the star's core shrinks. That pulls fresh hydrogen from the layers around the previous core down into a region where the temperature is high enough for hydrogen fusion to go again, and we get actually more energy produced. We get the red giant phase. Now we're going to talk about the planetary nebula phase in this video. A separate video will discuss the supernovas. And then we still have to do the star's remnants, the very final stage of the star. So we've talked about this helium flash. When this happens, now the core again has an energy source. It's away from this degenerate state of matter. The core expands as the temperature goes up, increases its pressure. That pushes hydrogen back out into the cooler part of the star. It's not cold, but the cooler part of the star. And the rate of hydrogen fusion goes way down. So the star is not producing as much energy on the interior. That causes a decrease in the pressure in the interior. Gravity wins again for a while, and the star's radius decreases because there's less total energy being produced in the interior of the star. We now have less outward directed pressure than we have inward directed pressure from the weight of the material on the outside of the star. We get some helium fusion for 100 million years or so, creating carbon. Eventually that helium is used up, and the temperature for a star of the mass of the sun does not become high enough that carbon can fuse. Carbon has 6 protons and 6 protons trying to get together requires a very high speed, requires a very high temperature, and that does not occur for a star of the mass of the sun. So I just got to give you an explanation. Maybe you don't have a neighbor handy right now anyway. So I'm going to pause for just a little second while you think about that. Carbon does not fuse in a star as massive as the sun or a smaller mass, yet a little bit bigger than the sun. Carbon does not fuse. So we lose that energy source. And just for clear-cutness, let's call the division between low and high mass stars 8 mass times the sun. 8 solar masses. So, we're going to talk about in this video what happens to the life of the star for the case when it's less than 8 solar masses. So, this star does not fuse carbon all the way up to iron, producing the elements in the periodic table. As we get towards 8 solar masses, it might be able to fuse carbon a little bit, and I don't remember. But it's not going to go through the full process of bringing us up to an iron core. So let's just say there's carbon there. And again, this is a situation that's going to take a long time for the low-mass stars. The low-mass stars have less fuel than the high-mass stars, but the low-mass stars don't burn that fuel very fast. Their luminosity is dependent on mass to the 3.5 power. So when the mass is small, luminosity is small, they have a small amount of fuel, but they don't use it very rapidly at all. So they have very extremely long lifetimes for the low mass stars. So we're in this giant phase for the star, and in this giant phase, we have the core. Again, the helium is being depleted a little bit in the core when it leaves the helium main sequence. And again, we can have shells of fusion around the core, a helium fusion shell and a hydrogen fusion shell. And again, with the compression of material at the core, the temperature is higher. So these fusions burn at a faster rate. Burning equals fusion. That the fusion process proceeds at a faster rate, creating again more internal pressure in the star. And now we can push the star layers out to the supergiant phase, or very big red giant phase, similar to what happened when the stars left the main sequence, when we got the red giant. Now we're leaving the helium main sequence and we're going up into the supergiant category. In these very large stars, the outer layers of the stars are very far from the center of the star, and gravity depends on distance. So atoms out in this extreme edge of the star's atmosphere are not pulled back very strongly. And the light from the star, and if the star is pulsating a little bit, that can push the gas away from the star. And it turns out these stars can lose significant amount of mass. And one solar mass, that's a significant amount of mass. And in 10,000 years, this gas just drifts away from the central star. It has escape velocity. It's moving away from the central star. What this does, it moves the outer layers of the star away, and we can now more see the hot core. So how do you think this star would be located on the HR diagram? Temperature goes to the left, increases to the left. This star is going to gradually be plotted more and more to the left on the HR diagram as the hot core is more and more revealed. And the ultraviolet light coming from this very hot core is able to ionize the gas in the that was pushed out away from the atmosphere of the star. So this ionized gas, the electrons are recombining, and different emission lines are being emitted by the atoms as the electrons recombine with the nucleus of the atom. And we do see colors when we look at these objects in the telescope, and they look significant size, as big as a planet in the telescope. Are they the size of planets? No, they're much, much bigger. The planets are close to us. Here we see something that is apparently the size of a planet in the telescope, but it's much further away, and consequently it's a much larger object. So here's a photograph of a young planetary nebula. You can see material that's coming away from the core. You can see these kind of waves of atmosphere that are moving out away from the star. Another planetary nebula, the Helix Nebula. And you can see just a dim point of light in the center there, and that's the remnant core of the
It's going to be a white dwarf.
supergiant. So we have this hot core being revealed, and again, colors coming off, emission lines from atoms as the electrons recombine with their nucleus. So our sun is going to grow in size and eventually become a planetary nebula as well, with its atmosphere being pushed away from the central core.
It's gotten more dangerous to be a woman in Texas.
And it's Ted Cruz's fault. So whether you were
Here's on the HR diagram what's happening here. So we've had the star leaving the main sequence, go up to the red giant phase, helium flash occurs, we get the helium main sequence, and then the star grows in size again. We get on to the larger than the giant stage. This one doesn't go extremely large, but larger than the giant stage. And after that, we're pushing away the atmosphere of the star, and the more revealing the hot core of the star system. They have this planetary nebula with a very hot core, and gradually, since there's no fusion going on, gradually that core cools off, and we move into the white dwarf stage.
Let me pause what he's got going on there, okay? So he's drawn the HR diagram here. You got your main sequence, okay? A star like our sun you look up here, okay, is when fusion stops, right, it's going to cool down. And it's going to become dimmer, okay? And it's going to do that until, remember, as it's getting bigger during this, but it's not as bright until we get this core that's beginning to do fusion. And that's what he's referring to as the helium flash. At that point, during the helium flash, it's going to get hotter, right? Which means we got to start heading back left, right? And it's also going to get brighter. Excuse me. Let me take that back. It's getting hotter, but it's going to be less bright as it contracts slightly. So it begins to, we have a change that happens here. As soon as that happens, we very rapidly move back down. Your textbook, I like how it did it a little bit better. Your textbook has this as kind of a dotted line coming down because this happens so fast. He keeps referring to a red giant main sequence. I haven't seen that in the literature, but basically, we then enter a second phase where we're getting bigger. And then now, where he's picking up here is as the planetary nebula moves off, you can see that core. The star is essentially changing completely. Those outer layers, which are cool, they're gone. What's left, and those outer layers which are cool and bright are gone. What's left is just a very dense white dwarf. Super hot, not very bright. And so as you're watching, if you were just watching a star for millions of years, right, its brightness and its temperature, you're going to see the brightness diminish as those layers go away, and as the brightness, well, he's got it kind of going like this, which is probably more accurate than what I've got. As that brightness diminishes, that's because those layers are going away. Well, also you're going to see more heat because it's only the core left. And now you're going to kind of end up down here. Of course, we know this is the red giant region, right? Let me erase this. Here's main sequence. This is red giant territory. And this is white dwarf territory. Okay? Here's main sequence. Okay? 90% of its lifetime here. Last 10%, we're doing something like this until we get to the white dwarf. Okay? Significant changes and things that are happening here. This step right here is as we leave the main sequence and become a red giant, right? So we're becoming, I'm going to label these, it'll help. A, B, C, D, etc. Okay? So this is going to be our A. This point here is going to be our B. C is going to be down here. This will be D. This will be our E. This will be our F. Okay, I'm going to label these. So A is going to be becoming a red giant. B is going to be what we call our helium flash. That's when the cores become so dense, so hot, that it's hot enough to fuse helium into beryllium, which doesn't last very long. We'll talk about that. Nanoseconds, and then ultimately into carbon. Okay? C is the period of time while helium is fusing. D is going to be, how do we want to say this? Becoming a larger giant. So this is after the heat, you know, we enter this phase because we've run out of hydrogen. We enter this phase because we've run out of helium. Okay? So we do helium fusion until it's gone. Once all that's exhausted, again, there's no more there's no more I don't want to say this. You've got the core is going to contract even further. It's going to heat up. We begin igniting other layers of hydrogen fusion, and so it begins to press up. And then when we get to this E, you know, we're looking at planetary nebula. And maybe a transition. And then when you get to F, you're looking at a white dwarf. Since the majority of stars, the vast majority of stars, are somewhere around the size of Earth, within a few solar mass units, most stars go through this phase. If you were big enough, if you were somewhere around 7 solar mass units, after you run out of hydrogen, you go to helium. After you run out of helium, you can start fusing heavier elements, as long as you have enough mass to create enough heat to sustain that. But if you're not massive, at some point every star just runs out of energy to fuse anything hotter. Okay? And so, depending on your size, you can get bigger than this. And you can have a whole series of these expansions and contractions and expansions and contractions. But all of them are going to experience something similar to this. Now here's the key. When the time comes, I'm going to give you a graph like this. I'm going to give you this graph. And you're going to have to tell me, like, okay, what's happening at A? Well, we're becoming a red giant. Well, what happened at B to change us from the red giant phase? Well, helium started fusing. Okay. Well, what happened at C? Well, I ran out of helium, right? And so, this is where I'm actually using my helium. And then at D, I'm done with that, and I'm continuing to expand. E, planetary nebula, this drifts away, and we slowly fall into our regular white dwarf thing. I don't know what is going on with my phone. I do apologize. We have turn it to that. Okay. Make sense? A little bit? Questions? You got questions? No? Will later?
Yeah.
Probably? Okay. All right. Well, let's finish up with this guy, and I'll show you a couple more things.
The carbon core. So we come down the main sequence, gravity winning here. We get extra pressure in the interior as the hydrogen fusion shell takes place, pushes it up to the helium, to the red giant. Helium flash occurs. Internal pressure drops back down as the shells of helium and hydrogen don't produce as much energy. Then we go up larger again as the process runs out of helium in the core, and we get the higher temperature in the core. We get shells of helium and hydrogen fusion giving off some more energy. And then the atmosphere of the star is ejected, pushed away, and we reveal the hot cores. We go left on the HR diagram for the surface temperature properties, and finally cool down to the white dwarf. We'll talk about in a different video. Here again on the HR diagram with some of the times, and you might notice a trend here. The processes happen more rapidly as we get towards the end of the life of the star up to this point, and then they're not showing the white dwarfs on this diagram, but those are very long long times down there as well. So some photographs of planetary nebula, one called the Ring Nebula, very famous and very lovely view in a telescope. And it's not spherical exactly. It depends on the shape that you see in the telescope is a little bit on how the pole and the equator of the star are arranged in comparison to the Earth and how this material gets pushed away. But again, the central star here that's very hot and ionizing gas inside here, this hot star giving off ultraviolet light. But where we do have more gas, we see more light coming. So it's a little bit like a soap bubble, but I don't want you to leave you with the impression that the planetary nebula are spheres. They're not just spheres. It's more complicated outflow of gas from the star than just a spherical shape. But where we do have more gas, we get more light. So the atmosphere that's been pushed away is a little denser, where you see the more light. Here's some other photographs of planetary nebula.
Okay, what's at the core of each one of these? What's at the center? A white dwarf. Okay, that's at the end of it all. As this thing, expands and expands, and it's so far away that the light from the white dwarf doesn't radiate the gas anymore. That's literally all that's left. If you were less than 8 to 10 solar mass units, this is what will become of your star.
We should convince you, planetary nebulae are not just spheres, but can be very complicated, and we can have periods of higher outburst or pushing away of the atmosphere of the star and get some rings, more complicated ring structure in here, some lobes of atmosphere that have been pushed away, but a nice arrangement of different kinds of shapes from these planetary nebulae. And again, this is towards the end of the life of the star. It's not too long. It's going to be not visible to us. But in this stage, this atmosphere is being energized by the central star and shines brightly and gives us these, almost they look like planets. When they were first seen, they were thought to be planets, but then astronomers realized they were not moving through the star field, so like planets do as they orbit the sun. They're very, very, very far away. They're like star distance away, and consequently don't move through the constellations. But planetary nebula, gas that's expanded, it used...
All right. Two more things to look at. We'll do this one first.
All the atoms in the universe heavier than hydrogen and helium are forged by stars.
Stars are really interesting. They don't just sit there. They know because they last so much longer than we do. We think they're permanent.
Stars are the ultimate alchemists. They turn light elements into heavier ones. They get the energy that they need to glow that way. A star begins its life made out of hydrogen and helium mostly. About 70% hydrogen, 28% helium in the case of the sun.
In a star's core, the temperature and pressure are so high that hydrogen atoms fuse together to make helium. Hydrogen fusion releases prodigious amounts of energy, the heat and light of a star.
That's the story for 90% of the life of a star, fusing hydrogen to make helium.
Eventually, though, the star runs out of hydrogen and begins to fuse its stocks of helium, making yet heavier elements.
And so the way it works, and it always works this way, is that it contracts and it gets hotter. And if it can find something new to burn, whether it's the kitchen sink or coal or whatever, it'll burn it.
Helium is taken 3 at a time to make carbon.
You can add one more helium to that carbon and make element number 8, oxygen.
That's a tremendous step forward. You get carbon and nitrogen and oxygen made in stars.
Now this is great because on the board we already have the principal elements of life.
Organic chemistry is the chemistry of carbon.
Carbon fuses next, and still heavier elements begin to form.
Sulfur, argon, chlorine.
Potassium, calcium, scandium. The pace of this gets faster and faster.
Back in the middle, silicon is starting to burn at 3.5 billion degrees, stupendous temperature.
It makes titanium, vanadium, chromium,
Manganese, cobalt, nickel, and iron.
Iron is really the end of the road. It's sort of the nuclear turnip out of which you just cannot squeeze anymore.
It's the end of the game. A star that has relied on fusion has come to the point where it has nothing more to spend.
The star is suddenly caught in a disaster. There's radiation going out from the outside, but deep in the inside, there's no more fuel.
Iron can't fuel the stellar furnace. And so, when a star builds up too much iron, it dies.
The core collapses, it bounces,
And it begins to move out, first slowly and then faster and faster.
and that sends a very sharp wave back out through the star.
And now what was falling down is going out, the whole thing blowing up. And you've made a supernova.
The supernova explosion can be as bright as 4 billion stars like the sun.
A stupendous explosion.
Such outrageous energies overcome the iron barrier, cooking atoms into all the rest of the elements on the periodic table.
So starting down here, you can go copper,
Zinc,
gallium,
germanium,
arsenic,
zirconium, niobium, molybdenum, technetium,
strontium,
rhodium,
potassium,
antimony,
terbium,
fluorine,
fluorine,
iodine, xenon,
francium,
barium, lanthanum,
tellurium,
cerium,
neptunium, xenon,
thorium, protactinium, iridium. None. That's enough elements.
All right. So what they're discussing there is, in every star, whatever phase, gravity's contracting that core. If there's enough gravity, there'll be enough heat produced to begin fusion, right? We know that in main sequence star, it's fusing hydrogen into helium. When it runs out of hydrogen, it begins to contract, heat up again, you'll get helium fusing into things like carbon or possibly into oxygen. Remember that for these smaller stars, that's the end of the line. But if you have much larger stars, then it'll stop fusion again, it'll expand on the outside, but the core is contracting, it'll heat up even more, and now it can fuse carbon into things and oxygen into things. It keeps doing it. As long as there's enough mass, you can fuse anything up to iron. Iron does not work. See, here's how fusion works in general is it does take energy. You have to input energy to get protons and other atomic nuclei to fuse together. But when they do, you convert mass into energy, and you release more energy than it took. And so you can these are a constant fuel source. That works for everything from hydrogen until you get to iron. Iron, it takes more energy to fuse it than you can possibly get. It takes energy to fuse it. You don't make energy when you fuse it. And therefore, you begin to pour all your energy into making iron, but you don't get any back out. You just run out. And then all you're left with is gravity, right? We want to talk today, the last little bit here, about fusing hydrogen to helium, which we know about, but then fusing helium into bigger things, okay? So this is atomic number 1, this is atomic number 2. If I combine 2 heliums together, what do I get? Atomic number 2 plus 2 is 4, right? So helium plus helium. Suddenly realized I need to be doing this over here because of where the camera's at. For those who are not online. So I'm going to take this, or those who will watch this online at some point. Okay. Hydrogen 1 plus, hydrogen 1 plus hydrogen 1 plus hydrogen 1 gives me helium. Atomic number 2, atomic mass of 4, okay? That's a helium nucleus. This is also referred to as an alpha particle. If you're ever looking at radiation, and they talk about either beta decay, gamma decay, or alpha decay, this is alpha. This is alpha radiation. It's huge. These are huge particles that are shot out during radioactive processes. So, if I take 2 of these, and I add them together, if I have enough energy and pressure and everything else to collide these 2 things together, what will I get? I'll get beryllium. Atomic number 8. Atomic mass, atomic number 4. Atomic number 4, atomic mass 8. Okay? Here's the thing about beryllium. In this configuration, this is extremely unstable. This lasts like nanoseconds. Let me look at the time that this exists for. I mean, the half-life of this is ridiculous. I didn't highlight it, so, oh wait, maybe I did. You probably don't care anyways, do you? I didn't highlight the time. It's something on the order of like 1 × 10⁻⁹ seconds for a half-life, like literally a nanosecond that this exists for. Because the formation of beryllium requires energy, but it does not produce any energy. No, you don't get the whole E = mc² happen with the formation of beryllium. It's completely unstable. And so beryllium splits back apart into these 2 things almost right away. You can get them to stick together, but you can't get them to stay. They won't stay very long at all. And yet we have to get beryllium to get anything bigger. So if I can get them to stick for a nanosecond, and that's it, and yet they are an essential step in making everything else that's bigger, it tells you that there's got to be something else involved here, right? And so they refer to this as the triple alpha. So in the triple alpha, you don't just take 2 of these, you have to get 4 of these. All right, they say 4, I meant 3. And that will form carbon. C6, 6 protons, 12 neutrons. There are lots of isotopes of carbon. Carbon with 6 neutrons, with 7 neutrons, with 8 neutrons. But the most common by far is the one with 12. It's because this is the most readily made thing in during the helium fusion stage of a red giant. So again, if I put 2 of these together, they'll form this for about a nanosecond before it splits apart. But if during that nanosecond I happen to hit it with another helium, then carbon will release energy. This will be energetically stable, and it will hold together. And so you see a lot more carbon than you do beryllium. You see it a lot more in stars, you see it a lot more on Earth, because this is not very stable. So let me show you a little video on that, and then we will be done. And yes, I know this has been tedious.